Hi. Welcome to a brief overview of our work on mixed reality interfaces for task planning and execution. The key idea here is that in domains where the full expressiveness of natural language is not required, such as on the factory floor, we can achieve better interaction using visual cues for the purposes of safety and improved collaboration. The key challenge in human-robot communication is the impedance mismatch in how they represent and share information. On the one hand, robots cannot directly infer the human state, while on the other, they find it difficult to express their own beliefs and intentions easily. Natural language is noisy and ambiguous, and perhaps not the best option in restricted settings that can be engineered for more effective communication using, for example, the medium of mixed reality. A holographic vocabulary allows communication using intuitive visual cues using the environment as a canvas. Here is an example of an operator talking directly to a robot involved in a collaborative assembly task in terms of which bolts go into which locations on the assembly board. The entire coordination occurs without any speech instructions. While mixed reality interfaces are becoming more popular every day, most of the existing work has only focused on visualizing the current action under execution, with most of the approaches tailored for motion planning and visualization of trajectories. Instead, in this work, we investigate how these principles translate to longer-term interactions and task planning in general. Specifically, we look at how projections in mixed reality can be used to disambiguate intentions during plan execution and generate behaviors that would be easier to disambiguate at the time of execution, and externalize the state of the robot to achieve common grounds with the human in the loop. We begin by looking at disambiguation of intentions at execution time. First, we need a vocabulary that can describe features of a plan in the form of symbols afforded by the mixed reality workspace. To this end, we define action projections which tell the user that the robot is going to do a specific action at some point in future, state value projections which tell the user the value of a particular state variable in future. This very simple vocabulary does not capture sequences or even when these events will occur. The good news is it is domain independent and still affords a rich variety of interaction patterns that we will explore next. So how do we disambiguate intentions at execution time? The robot here is trying to execute a plan. However, there are things it could be doing. It represents the salient features of these plans in terms of resource profiles associated with its own plan and the set of possible plans. It then identifies the most disambiguating feature and projects the intention associated with it to the human so that it is easy to tell now which plan it will end up executing. Now let's watch this in action. Here, the robot's internal goal is to form the word brat. Given the letters available to it, it can form other words. Consider boat and coat. The robot indicates that it is planned to pick up the block R by projecting a green bobbing arrow on top of it, since R is only part of one possible plan. This only solves part of the puzzle. Full disambiguation is not guaranteed to be possible with this vocabulary. And the human may not like the resulting plan even after full resolution. Once the robot has deployed its intentions, the human can come back and manipulate those to shape the behavior of the robot in real time. All this occurs without any speech act, by using annotating the environment with information on how the world will evolve, and allowing the human to interact with them in real time. Now let's watch this in action. So far we have only tried disambiguation of intentions during plan execution. We now ask, is it possible to use this ability to generate plans that are easier to project in the first place? This brings us to projection-aware plan generation. The key idea here is to, during search, pick actions that minimize entropy of the probability distribution of possible plans from the current state. This will cause the planner to add projection actions in the plan that can cause maximum disambiguation. However, the entropy is hard to compute. Instead, we approximate it by computing disjunctive landmarks to the goals and finding membership of each projection asset in the relaxed plan. The fun part of this approach is that the robot can now trade off the cost of a plan with the ease of communicating it via projections. This means that, if necessary, it can produce plans that are longer but easier to project. Also, contrary to previous works on generating predictable behavior, mixed reality allows the robot to foreshadow intentions instead of relying on physical interspeech actions only. This is where the power of mixed reality really comes forth. Now, let's watch this in action. A higher value of alpha drives the robot to generate shorter plans which may not be completely disambiguated. For example, act and cat are both possible after projection on C. With lower alpha, the robot produces a longer plan, to brat, that can be completely disambiguated by projecting a future pickup on R. So far we have focused on plans assuming that the model of the robot and the human are aligned. Mixed reality projections can also be used to achieve common grounds by externalizing the beliefs of the robot. This brings us to the notion of projection-aware model reconciliation. The core idea of model reconciliation is to update the mental model of the human in the loop, so that optimal plan in the robot model is also optimal, and hence explicable, in the updated human mental model. It is a way of making sure two collaborating agents can remain on the same page with respect to a task, when their models are not aligned, or diverge over time. Now, let's watch this in action. Here, the goal of the robot is to create a tower of height 3 with the red block on top. An expected plan here involves spotting the green block on the blue block, and then putting the red block on top. But the robot takes a roundabout route by unstacking the red block first. This, however, makes sense once the robot annotates the blue block as unreachable. So, to recap, we looked at how the medium of mixed reality can support a wide range of interactions in the scope of long-term task planning and execution. Specifically, we looked at how projections in mixed reality can be used to disambiguate intentions during plan execution, generate behaviors that would be easier to disambiguate at the time of execution, and externalize the state of the robot to achieve common grounds with the human in the loop. Of course, the power of mixed reality interactions extends beyond human-robot interactions to human-AI interactions in general, such as in vehicle-to-vehicle communication, especially with autonomous vehicles, and intelligent decision support systems in mission control situations with multiple human commanders in the loop. If you are interested in learning more, follow our work at the link on the screen. Thank you for watching.